Hello. This in this video, I'd like to talk to you about transformers. So this was the both weeks 3 and 4 in the program I'm following at the Machine Learning Institute at Founders and Coders to become a machine learning engineer. So what were the objectives of these 2 weeks? We were looking to understand the main components of the transformer. So as we will see later, is made of several blocks, and in each block there are different components like attention mechanisms, queries, keys, etc. We're going to look into more into that. So as I mentioned, the understand also the importance and the significance of the attention mechanism in the transformer block. We also implemented a small to medium transformer model, so from scratch using PyTorch. We weren't using any readily available models. We trained these for long periods of time. So as you know, transformers could have billions of parameters, so they take a lot of time. And we learned how to do checkpointing, continuous evaluation. And thereafter that, we scaled the model, so from small, medium to billions of parameters, or several millions of parameters actually. Billions of parameters. We're starting to talk about some of the most performant models out there, like GPT and Llama. So Llama 2 is about 75 billion or 7 billion, I think. So here we're staying under 100 million, but still, for the scope of what we're doing, this could be considered as a scale up. Then how to track the metrics even when the size of or the number of parameters increase, and obviously training that on GPU, because otherwise it would be very complicated. And during this process, monitoring the progress, training loss, accuracy, and maybe other metrics using weights and biases, which is a much more it's a much more what's the word, professional way maybe of monitoring the progress of the learning of the model. Right, so quick word about transformers. As I said earlier, transformers now are one of the most important architectures, or the most performant architectures in natural language processing, in large language models. Most of the performant models that we see out there now use the transformer architecture. Now, the transformer could be made of two components: the encoder, which is called BERT, and the decoder, which GPT, which ChatGPT uses, that you can see here. However, it seems like most of the state-of-the-art models actually use a decoder-only architecture. So they just skip the encoder element and they feed everything into the decoder. So you would only see the element to the left here, and the element the element to the right, and the element to the left encoder is not required. And as you can see, what we did throughout the week is we familiarized ourselves with the different components of the transformer. So the embedding, the positional embedding, which means basically is how do you translate the importance of the position of the word in a phrase to the model. So the model needs to know that the position of the word actually has a significance, and it needs to learn that. So insert that at the input level, and then we get into the transformer block. So this is what we call a transformer block. There could be several of it attached sequentially, one after the other, and then within each block you would have different elements. The attention mechanism, which you can see in orange here. There could be a masked attention and a non-masked attention, and what we mean by that is, if it is in a masked attention, you would mask, so each entry, instead of it being the entire phrase, let's say, you would give it the first word and hide everything else. Then in the second example, you would give it the first word and the second word and hide everything else. And then the first word, second, third, and hide everything. So that's what we call masked. In the normal, let's say, attention unit, which for example you would see here in this architecture, you would just give it the entire phrase without any masking. Multi-head means this orange thing. What happens is that the input is spread across multiple heads. So these, you can imagine these like happening in parallel. So the input would come, get split into three heads, go into three heads, and then get added back up and joined after it goes through the heads. You could have one head if you want, but you can have four heads, eight heads, as much as you want. After that, There's a layer where you would add the input to the attention unit to the output of it, and then you would normalize that. So these all have reasons in terms of the stability of the algorithm and the calculations, etc. Then, if you would have an encoder, there are certain inputs that come from the encoder, and then some of them would come from the decoder. And these three arrows here, they correspond to something we call query, key, and values. There's a reason why, it's not just a naming. There's a reason why they've given in three names, even though they actually, as you can see here, they stem from the same original value. So as you can see here, it's one single value that gets split into, I think, query and keys. Or if you look at here, for example, the input we have gets split into query, keys, and values. There's a reason to do that, and it's very, very important to pay a lot of attention into these, because the way the calculations, the matrix multiplications are done is quite tricky, and and a very good understanding of the shapes of each of these matrices and how they get transposed, inversed, etc., is extremely important if you're trying to build a transformer from scratch. So after we've done that, so after we've done through the max attention and then the normal attention, and we go through the adding and the normalization layer, once all of this is done, we have a feed-forward network, and then after that, again, we go back to add normalization, and then in linear and softmax, and that finally would give a probability vector. So as you can see here, this is an example of basically how we've coded everything from scratch. So this is an example of code snippets from the work we've done. One thing that would be interesting to consider, and that I've noticed during coding, is actually you need to model three blocks, okay, like with classes, do them really well, and then once you've built these three blocks, you can build the entire transformer just by creating more instances of these classes and just placing them in the right position. So these three blocks are the embedding layer, how you get the embeddings right. So when you receive an input, how you process that, so you transform it into an embedding, and then you add the positional embedding to it. After that, you have the attention layer and the feed forward layer. Once you've coded these three, like one after the other, just these three, the entire architecture that you're seeing here to the left can be built using a combination of these three code blocks. So that's quite interesting. So instead of getting lost in this what looks like a very complicated architecture, you could just focus on getting these three units right, and then you can scale your transformer up as much as you want. And the more layers you add, the more parameters your model will have, and the larger it will be. So yeah, that was quite interesting, quite interesting observation. And everything else, by the way, that you see here that is not in a block, like, or in a rectangle, these usually are one-liners in PyTorch. So the add and normalization layer is actually a one line from PyTorch that you can use that would do these for you. You would just need basically to give it the right input. So as you remember, the add and norm layer requires two inputs. It requires the output of the multi-headed layer as an input, but also the input of the multi-headed layer as an input as well. So yeah, let's pay attention to that. Right. So once we've done the coding, I started training the model and experimenting with training just to get an idea of what's going on. What you're seeing here first, I started with the CPU training. So you can see here the first one. I just went for the simple transformer with one head and with one head. So I have about 20 million parameters, and I was training it on the CPU. And as you can see here, the accuracy was, still going up, but still less than 50%. But that's it's interesting when we talk about accuracy when it comes to transformers on large language models. That's a challenge. I feel like, how do you actually evaluate your model? But I'll get to that later on. Then after that, I started playing with the GPU. So again, I used the one head, and you can see here. Um, yeah, so it was still a one head parameter, but basically, sorry, one head transformer, or one head in the multi head attention unit. But I used a different number of parameters when it came to the embedding size, the vocab size, etc. And that showed me actually that it's not the number of heads that significantly increases the size of the model, but it's actually these parameters that you choose initially. So your embedding matrix, how many features you want in your embedding matrix. It's the vocab size. Do you want 15,000 vocab size or 60,000? And yeah, some of these parameters actually have way more impact on the number or the size of the model than how many heads you use. Um, yeah. So after that, I moved to, as you can see here, to four heads, and then eight heads. And for some reason, initially I had some issues on GPU. I think some elements in my code weren't done properly, in the sense that some elements were still on the CPU and others on the GPU or something. So it was crashing my model. So as you can see, both of them here were stopping at the same time. So I looked into that, I fixed that. But it was again interesting to see, like, here we have four heads, 20 million parameters. By adding four additional heads, we only add 1 million parameter. But if you change the initial parameters that I spoke about, you could have easily a jump from 1 million to 20 million. So yeah, the model started learning. That's the important, is was to train it and to track it on weights and biases. This is from weights and biases, and try to just understand what it's learning. So here, for example, what you see is the output of the attention matrix. I've compared a few. So for example, now you can see the left, the initial attention layer. It was randomly initialized, so you can see everything is almost like a uniform color, really, with like really light shades here and there, is except at the top, because at the top, when you have one element, one word, then its value is one. When you have two, it's each one would be anywhere between 0 and 0.5, I suppose, or actually anywhere between 0 and 1. But then as we go further and we have more parameters, their values will be much lower. So yeah. But after training the parameter that you can see here, you can see that now the model is paying attention to different elements. And by the way, here in these images, each row corresponds to an input or a training record. And each training record has a number of words. So basically, here at the zero row, we have just one word. At the first row, we have two words, and so on so on and so forth. So as you can see, as the training record becomes larger, the model starts paying attention to different words, which is quite interesting. It still seems it's still, we haven't got to the level to try and explore what does that mean, why is it paying attention to certain words and not. But it was interesting to gain this understanding of how the attention unit works, and it actually pays more attention or gives certain weights to certain words in a phrase more than to others, and that actually gives it the powerful outputs or accuracy that it gets. Here's another example. So now both of these figures that you're seeing are trained models. To the left, we didn't add positional encoding. To the right, we added positional encoding. And again, you can see slightly the difference here with and without. With positional encoding, you see that it's more homogeneous, more uniform. Whereas if we didn't add positional encoding, you can see that there's a lot of words that are more distinct, are being paid more attention to than others, which is quite interesting. But same as before, it's not clearly understood what does actually what's the meaning of that, what are the mechanism, why is this happening, and what does it mean. And then finally here, we're looking at different heads. So what are different heads in our model learning? So you remember we could add 4, 8, 9 heads, and each head will learn something different. So again, this shows the concept of how different heads learn different things, and by combining the learning of different heads, you could have a better outcome or a better accuracy from the transformer. So So yeah, you can see here to the left, this model, for example, is paying a lot of attention to the word in this location here and here, whereas to the right, this head is not really paying attention to these words. So that shows you this concept of attention. Right. So after that, once I was happy with the model and everything on a simple level was actually working like I wanted to, that was the right time to start scaling up. So now, after scaling up and adding more parameters, more attention layers, more heads, etc., the model we reached was about 78 million parameters. And you can see here, if you remember what I mentioned earlier, that the choice of the input parameters have a higher significance on the total size of the model. So you can see that the embedding layers, how large they are. So these two layers have, let's say, 20 million parameters each. So 40 million in total, just these two embedding layers. So yeah, that's quite interesting. Then we got a few million here, and then a few million spread around. This is a yeah, 2 million here, another 1 million. So yeah, it's getting quite large. And I trained it actually on. I was interested in knowing how fast different machines are. So, for example, it was taking about 20 minutes to train per epoch on the Machine Learning Institute GPUs. And what I noticed actually is that my laptop's GPU was 10 times faster than the CPU when training it on the CPU, and the Machine Learning Institute GPUs were four faster than my laptop's GPU. So yeah, that was quite interesting. And we continued um, training the model and monitoring different parameters. So I was looking at the training loss, the validation accuracy, and the blue score. And the reason I started looking into these is because I still don't understand really, how do you evaluate a large language model, a large natural language processing model? What does accuracy mean when we're talking about words and predicting the right or the wrong words? So I started researching into different parameters. Blue score, or the blue parameter seems to be an important metric that is used with large language model. But what I've done here is I just applied it, used it, but I still need to have a better understanding of how it functions and how to interpret the results. Overall, you can see here that the validation loss is going down, even though it's a bit bumpy. But I can smooth. But if I smooth this out, we would get this nice decrease that we usually like to see in loss functions. Same thing for the training loss, and you can see the validation accuracy was also going up, reaching about 85%. In terms of the blue score, so as I mentioned earlier, I was interested to know like what does a score of 50 mean, 30 mean, etc. And you can see here there's a description of the meaning of the score, or each interval in the score. So it goes from useless results if the blue score is less than 10 to quality, often better than human, um, human performance, when your large language model is obtaining a score larger than 60. However, I applied the transformer I was training it on translation data. So basically, I was feeding the model Italian and English, and then asking it to make a translation from Italian to English, and then I was comparing the model's translation to the labeled data, basically. So if you look at this example, this is one example of testing the model. In that instant, the validation accuracy, was about 84%, and the blue score was about 36. So just to remind you, 36 means understandable to good translation. So at this level, with these parameters, it seems like the model was doing understandable to good translations. And actually, if you look at it, it actually is pretty good. So I gave it here a user prompt in English. I went to school on Friday. I played with my friends. I came back home in the afternoon, and that was the outputs of the transformer. Sono andato a scuola venerdì. Io ho giocato con I miei amici. Sono tornato a casa. And I looked into Google because I don't speak Italian, and it seems like it's done a really good job. So this is the basically the phrase from my model. So I just copied this phrase here into Google Translate, and that's what Google Translate gave. I went to school on Friday, I played with my friends, I came back home. So that's exactly the initial user prompt, except for that last phrase in the afternoon. So the model wasn't catching it. But basically, what I want you to pay attention to is that this is a quite good translation, bar the lack of the last three words, and the blow score was 36. Understandable to good translation. But then here's another example. In this example, the validation accuracy is even larger, and so this one here in the top is the one you saw on the previous slide, and this second one is where I got a better blue score. So blue score here was 57, and if I go back, 57 means what? Very high quality, adequate, and fluent translation. So I was like, yay, that's amazing. But then I gave it the same phrase. I went to school on Friday, played with my friends, I came back home in the afternoon, and this output, this is what it gave here. I put that into Google Translate. So this phrase here, which is the Italian translation that my model came up with, and here's what I what it came actually. I went to school on Friday. I stole with my friends. I came home. I went back to school. So it's really rubbish. It really didn't do a good job at all. It's useless. At the same time, the blue score was 57. So, so yeah, I think there's an issue here, and I need to get a better understanding of how does evaluating large language models work. We had someone actually from DeepMind that came, and that's basically what he does, and he said that they use a bundle of metrics, and all these metrics need to be going up in the training and the validation process for them to judge that this is a good or not good performance. They do not depend on human evaluation. They don't like print out examples like I've done here and see is this good or not. So I need to do more research into that, understand what are these bundle of parameters that they would use, and I would like to include that in the next version or next cycle of me working on large language models. So, to wrap up, basically I reflected, at the end of the week on what worked well in during this week. What really worked well, because at first we were a bit like, wow, this looks quite complex, especially when we looked at the architecture and started reading how it works and all the matrix multiplications. But actually, I was successful at the end of the week, and what really worked was starting with the most simple structure. So I really tried at every when you are coding, there are certain stages where you have to make a decision in terms of complexity, and at every stage I was making the decision to go with the simple. And so if instead of doing immediately four heads, I would do just one head. Instead of doing multiple layers, I would do just one layer. And I was moving very, very slowly. I was being like really a maniac in understanding the shapes of the input and the output of each unit of the transformer block. So I was moving very slowly because I really wanted to get this right. Sometimes doing calculations by hand just to make sure I understand how the shapes are changing and shifting and resizing, etc. And then every time I felt like, okay, I got it to a stage and it seems to be working, then I would add a level of complexity one at a time. So add a level of complexity, test it out, make sure everything is working, no bugs, no errors, and then add a new one. And actually, remembering also, every time I just felt confident that, okay, this seems to be working and I got everything right, I just assumed like, okay, maybe I got something wrong, and I go check with others in the group, in the different teams. I would talk to them, see their approach, what they're doing, what problems they're facing, talk about my understanding and what I've done, and see if something maybe that I understood wrongly and I need to adapt. And sometimes it was literally all eavesdropping. So I would be sitting on my laptop doing some coding, and then I'd hear a team having a discussion, and then something catches my attention. I go join the conversation, and I actually found a few errors in my understanding. I think one of them was, I think something that has to do with processing the input data, and I was doing it in a wrong way actually. And by eavesdropping, I heard the team talking about the same topic and how they're doing it. I went had a chat and I found out that they were right and what I was doing was wrong, and I fixed that, and that helped me towards the end of the week. In terms of the lessons learned, this week actually, what I did is I made sure also at the beginning of the week to focus on having an extremely clean file structure and having everything on GitHub. And I realized how I had been underestimating the importance of that. The using instances, having very clean snippets of code or bulks of code one after the other was extremely helpful. Having everything on GitHub where I can always pull and push was extremely helpful in clarifying my head. Like my head was always clear and I was able to focus on coding and building. And I didn't have all this noise in my head and which version am I working on, which one did I send to my colleague, which one they're sending me back, which one. So all of that was dealt with GitHub. And also in my head, because my file and codes were very structured in a very clear and clean way, that helped my thinking as well. I knew which pieces of code I needed to use and how to put them together like a Lego. So that made me, at the beginning, it took a lot of time. So I spent maybe like 2 days just getting there. But then after that, I was going really quick, and I got, I finished the objectives of the week quite quickly. And the last point is what I mentioned earlier. I felt that I was using a lot of human evaluation to understand if my model was performing well or not, and I'd like to understand how is this is done in like in corporate, in teams, in tech, in the industry. How is this done in a very automatic way, in a very not commercial, maybe that's not the right word, but in an automatic way that allows you to judge that this model is now good and could be moved or can move to production. So yeah, another super exciting week. I was exhilarated at the end when I realized that I just modeled or coded transformers from scratch. They were actually doing quite well, relatively well, given that we had days to put them together from scratch. So yeah, I had the confidence that now I can do more complicated projects and move my set of skills to the next level basically. So yeah, super excited about the upcoming few weeks, and hopefully I'll have I'll do more of this in the upcoming weeks as well. Thank you for watching. Bye.